Hello everybody, welcome back. Welcome to AS Engineering Academy and AS online platform. Myself Prasad Megavarna. So here we are. So today to discuss about the switchgear and protection as a part of power system and in the course of RRB JE for electrical engineering students. So today we are going to discuss about some important concepts and some questions, some important questions related to the switchgear and protection as a part of power systems, right students? Now we'll see what is the actual syllabus of power system. The syllabus of power system is generation of electrical energy, transmission and distribution of electrical energy, power system analysis, and switchgear and protection and utilization of electrical energy, students. So today we are going to discuss about the switchgear and protection. So the RRB JE students and SSC JE students, in case of power system analysis, we are having completely the fault analysis part, right? Generation of electrical energy, transmission, distribution of electrical energy. So particularly fault analysis and switchgear and protection and utilization of electrical energy. This is the complete syllabus of power system. Now in this we are discussing about switchgear and protection, and if you see the syllabus of switchgear and protection, the switchgear and protection is consisting of introduction to the power system protection and electromagnetic relays and distance protection, differential protection and circuit breakers and protective switches we are going to discuss. So students, in place of introduction to power system protection, so in that case we are going to discuss about various concepts like we are going to introduce what are the components of the substation, right? So what are the various switches that we are having in the substation, right? What are the wave traps, what are the capacity voltage transformers, what are the isolators, earth switches, right? Current transformers, potential transformers, circuit breakers, everything we are going to introduce in the chapter 1. And along with that we are going to see what are the properties of the relays, what are the properties of the relays, all those basic concepts we are going to discuss in chapter 1. Later on we are going to chapter 2. So in the construction part are various types of relays. We are going to see the electromagnetic attraction type relays and electromagnetic induction type of relays also. And in case of electromagnetic induction type of relays, we are going to see the shaded pole type of relays, the watt-hour meter type of relays, and the induction cup type of relays. We are going to discuss about those things in the electromagnetic relays. And distance protection relays, so impedance relays, admittance relays and more relays we are going to discuss, and their characteristics and the applications we'll see there. And differential protection, so merge price scheme of protection we are going to discuss there. And there we are going to discuss about again percentage biased differential relay protection and protection of transformer and bus bar and the generators we are going to see in case of differential protection, right? And in case of electromagnetic relays, we are going to discuss about overcurrent relays as well as the directional relays also. And coming to the circuit breakers, so various concepts are various topics related to or various definitions related to circuit breakers and the protective switches like fuses, isolators and earth switches we are going to discuss in the chapter 5. This is the syllabus of this switchgear and protection, students, right? So majorly, so RRB JE students, we have to concentrate on theory concepts, right? So theory based questions we can expect in the power system protection, right? Suppose, so particularly we cannot say, so we can expect question from chapter 1 or chapter 2, chapter 3, chapter 4 or chapter 5. All the chapters are very, very important only. Clear, right students? Now, so we'll go for the next one. So what are the textbooks we can prefer? The textbooks we can take are the CL Wadhwa, that is Electric Power Systems by CL Wadhwa, and a course in power systems by JB Gupta, right? So these are the textbooks we can take for switchgear and protection, and in that we are having some practice bits also. We can practice those questions also, right? So after doing this one, so what we have to practice actually, right? So we have to practice some previous small ESC objective questions, some small questions, and previous PSC questions like so we can take some small questions only, right, from PSCs and previous state board questions, right, and previous SSC JE and RRB JE questions. So this is the practice set we need. Clear, students? See, right? So Durga Prasad, sir, please discuss overreach and underreach concepts, right? We will discuss about that one also, right? Overreach and underreach problems also we are going to discuss. Right, students? So this is what we are having. Students, first of all, in the introduction part of this course, we will see first of all what are the properties of the relays. Can you tell me what are the properties of the relays, students? So can you name some properties of the relays? Can you name some properties of the relays? So the properties of the relays are selectivity, right? Speed of operation, sensitivity, right? Reliability. All those are the properties of the relays, right? So you can see the properties of the relays. Properties of relaying system. Relaying system. What are those? First one is selectivity. Selectivity. Next one is speed of operation. Speed of operation. And third one is sensitivity. Sensitivity. And fourth one is reliability. Reliability. And the next one is, we can see the small size, size of the equipment, size of the equipment, and we can see the cost of the equipment also, right? So these are the properties of the relaying system we have to maintain, right? Now, so after maintaining this, right? So first of all, what is the meaning of selectivity? The meaning of selectivity is nothing but, so selectivity is nothing but, we can say it is the discrimination. It is called as discrimination. So the selectivity can be achieved by two aspects. One is the unit system of protection and non-unit system of protection, right? So discrimination means the relaying system, whatever you are going to design, that is able to discriminate between unit system of protection and non-unit system of protection. Unit system of protection means for the faults which are, that is the relay is going to operate for the faults which are within the zone of protection. Non-unit system of protection means the relay will operate for the faults within the zone as well as outside of the zone of the protection also, right? So whenever the fault occurs, right? So discrimination can be achieved by unit system of protection, unit system of protection, and non-unit system of protection. Non-unit system of protection. What are the examples of unit system of protection? So whenever a relay operates only for the faults within the zone, protective zone, right? So that is unit system of protection. Best examples we can see the differential relays are unit protective relays. Unit protective relays, and Buchholz relay is also a unit protective relay, right? So Buchholz relay we can take as the best example, and the differential relays. Buchholz relay are differential relays. Differential relays are also some of the best examples of unit system. And non-unit system of protection, the best examples of non-unit system of protection, so we can take the directional relays. Directional relays are the best examples, or overcurrent relays also we can take as the best examples of the non-unit system of protection. Right, students? Next one is the speed of operation. So a relaying system should have the highest speed or very low operating time, right? So very high speed and low operating time. So how can we control the operating time of the relay? The operating time of the relay can be controlled by controlling the back switch, position of the back switch, right? So that the speed of operation should be very high, such that the operating time should be very, very less. So to control the operating time, right, we have to control the back switch position where we are going to see that, right? And next one is sensitivity. the relay should have highest sensitivity. It is able to sense all possible faults. It is able to sense all possible faults. That is very small deviation in the quantity also it is able to sense. What will be the smallest possible thing, smallest possible variation in the operating quantity should also be sensible by the relaying system. And reliability means we have to trust the relay. It should have to operate whenever the fault occurs. Whenever the fault occurs. So reliability. So we have to trust it, right? So it can be achieved by, suppose you can see the relay has to operate. So whenever the fault occurs, and the relay should not operate whenever there is no fault. Whenever there is no, both should be satisfied. It has to operate whenever there is a fault, and it should not operate whenever there is no fault. Both should be acquired. Then only we can say the reliability of the relay should be very, very high. And size of the equipment, so we have to design the protective system with small operators only. That means with little number of equipments only we have to design the protective system, and cost should be very, very low. So these are the basic properties of the relaying system. Clear, students? Now, so we'll see the types of the relays. What are the types of the relays? The types of the relays we are having are types of relays. What are the types of relays we are having? Electromagnetic type relays. Electromagnetic type. Magnetic type relays. So in that, so electromagnetic attraction type, electromagnetic induction type, right? So you can take attraction type, and induction type we are having. In induction type again, so in attraction type also we are having several so classification. We can take balanced beam type of construction, right? So moving iron type of construction, those are the types of the attraction type of relays, right? And whereas in induction type of relays we are having induction disc type, and induction cup type. Whereas in case of induction disc type we are having two types of relays. One is shaded pole type of relay, and one is watt-hour meter type of relay. And along with electromagnetic type we are having the thermal relays, the static relays also there we are having, right? So we are having the thermal relays and static relays are also called as solid state relays, right? So they are the classification of the protective relays, right? So I have given so little bit number only. So we are having lot of quantities based on the operating time. So based on the operating time, these are based on the construction. So based on the operating time, we are having instantaneous relays, right? So definite time relays, inverse time relays, inverse definite minimum time relays, right? And very inverse relays, extremely inverse relays. These are the relays we are having based on the operating time. Clear, everybody? So based on the construction we have given here, right? You can write based on the operating time. Based on operating time. Based on operating time, we are having which type of relays? Instantaneous relays. Next one is definite time relays. Next one is inverse time relays. Next, inverse definite minimum time release, IDMT release, right? It is the combination of inverse type and definite time release, right? So up to some portion before the saturation we are having inverse time release, after the saturation we are having the definite time characteristics. We are having a very inverse release, and extremely inverse release. Extremely inverse release, right? These are the relays we are having based on the operating time. Clear everybody? Right. So now, Durga Prasad Sir, he is asking about what is the overreach problem and underreach problem of the release, right? Now, students, actually, after this classification, we are having one more classification also based on the application. So based on the application, we are having over current relays, over voltage relays, over speed relays, like that we are having different types of applications. And the directional relays, the distance relays, and the differential relays are the next category of the relays, right? So based on application, we can write based on applications, we can write over current relays and over voltage relays, directional relays, distance relays, and differential relays. Still we are having some more relays also. So over speed relays, over flux relays, all those are there, right? So in the syllabus what we are having here. So directional relays, distance relays, and differential relays. So particularly if we discuss about this distance relays, so the distance relays are, what are those? The impedance relay, reactance relay, and more relays. Impedance relay, reactance relay, and the more relay, right? So if you see the distance relays, Students, actually the universal relay torque equation. What is the universal relay torque equation? The universal relay torque equation, What is that? So the torque, the net torque in the relay is nothing but some constant K1 into I square plus some constant K2 into V square plus some constant K3 into Vi cos of theta minus tau minus K4. So K1 into I square is for over current relay, K2 into V square is for over voltage relay, K3 into Vi cos theta minus tau is for directional relay, and K4 is the negative portion, is for the restraining portion, right? So that is the restraining torque we are having. So if you see, this is for over current, this is for over voltage, this is the directional unit, and this is the restraining torque. Clear? So in case of the distance relay, the restraining torque is not provided by spring. The restraining torque will be provided by either voltage or current or combination of both, or we can say it is provided by the directional unit in case of distance relays. Whereas in case of the other relays, right, suppose if you see the overcurrent relays or any other relays, the restraining torque will be provided by the spring normally. But whereas in case of distance relays, the restraining torque will be provided by either the current unit or either the voltage unit or the combination of both. We can say that is the directional unit. Clear everybody? Now, in case of distance relays, we are having the classification is, first one is impedance relay, second one is reactance relay, and the third one is mode relay or admittance relay. Mode relay. So first of all, if you see the impedance relay, in case of this impedance relay, to get this impedance relay characteristic, so in the universal relay torque equation, some constant K1 should be positive and K2 should be negative and K3 should be 0 and K4 is always 0 for the distance relays, right? So K1 is positive, K2 is negative. So that what is the torque we are having? The torque we are having is some constant K1 into I square minus K2 into V square. So I told you positive portion is the operating portion, negative portion is the restraining portion. So that this is providing the restraining torque. The negative portion is providing the restraining torque. And the positive portion is providing the operating torque. Now tell me, what is the name of the relay? It is operating torque is provided by the current, so that we can say it is the overcurrent relay. But whereas restraining portion will be provided by the voltage, so that we can say the name of this impedance relay is also called as voltage restrained overcurrent relay. Right? Therefore, this relay is also called as, voltage restrained overcurrent relay. Right. So as the name suggests, it is the distance relay. So these relays always operates based on the set distance. So they will calculate the impedance or the V by A ratio in the set distance. So based on that distance or based on that set impedance value, they are going to operate. So that these distance relays will operate the distance relays operates based on the set distance impedance value. For example, if you are having the transmission line like this, this is the transmission line. For this transmission line, the line impedance is Z line, and we are calling this as Z set. This is the set impedance value. For this one, we are going to connect some relay. So this is the relay. This relay will measure both voltage and current. So it will take the ratio of V by I and it will measure Z relay. So that whenever this impedance seen by the relay, is less than that of this set impedance, then the relay will operate, right? So whenever the impedance seen by the relay is less than that of Z set, then relay operates. When Z relay is more than that of Z set, then the relay not operates. Clear everybody? So whenever Z relay is less than that of Z set, then the relay operates, and whenever ZR is more than that of Z set, the relay will not operate. And how to set this set impedance, Z set? Actually, under normal operating conditions, we are going to calculate the rated current of the relay, right? Suppose the rated current of the relay is rated current is nothing but I rated. I rated. And the rated voltage is nothing but V rated. V rated. Now, if you see the line impedance, what is the line impedance? The line impedance is the rated voltage divided by the rated current. Rated current. I rated. And we are calling this as the set impedance of the relay. So, whatever the impedance of the line we are having, that impedance we are calling it as the set impedance. Now, under faulted conditions, the current flowing in the line which will be more than that of this rated current, right? So, what happens? When fault occurs, the current in the line will be increasing and it is more than that of I rated. I rated. Now, this relay is going to see this impedance. What is that impedance? ZR. ZR. So, what is that? Which is nothing but, so V divided by whatever the voltage we are having in the line divided by I. So, what is the I now? The fault current. This fault current will be very high. That fault current will be very high. Whenever the fault current increases, also there may be drop in the voltage also based on the type of the fault, right? So, voltage may be decreasing and current is also increasing, so that what happens? The relay seeing impedance will be reducing. Whenever ZR is reducing, so we can say there is a fault in the system. If this ZR is less than that of the set impedance, then we can say the relay is going to operate. Relay operates. Then the relay operates. Whenever ZR is less than that of Z set. Whenever ZR is more than that of Z set, the relay will not operate. The relay will not operate. Clear everybody? So, this is the operating way of the distance relays. Now, first of all, we have seen the impedance relay. In case of impedance relay, the net torque whatever we are having is some constant K1 into I square minus K2 into V square. Now, this impedance relay, so Arif, overreach में fault zone के बाहर वो ऑपरेट करता है, yes, और अंडर रिच में fault zone के अंडर वे सेंस नहीं कर पाता है, yes, correct only. They are asking the explanation only. Perfect. Whatever the statement you have given is perfect only. So, this is the actual operating condition. If you see here, the torque, the net torque of the relay is some constant K1 into I square minus K2 into V square. Just check here, students. Here we are having the net torque in the relay is some constant K1 into I square minus K2 into V square. So, under threshold condition, the relay is at the verge of operation, therefore, the net torque in the relay will become 0. Therefore, some constant K1 into I square minus K2 into V square is equivalent to 0. From this one, K1 into I square is equivalent to K2 into V square. From this one, so K1 by K2 is nothing but V square divided by I square. Therefore, V by I, what is that? V by I is nothing but under root of K1 by K2. So, this is called as the set impedance. Where we are calculating the set impedance? The set impedance we are calculating under the threshold condition. Threshold at exactly verge of operation. So, beyond that which means that whenever current increases, the impedance seen by the relay will be reducing. So, that whenever, so relay looking impedance is less than that of set impedance, then the relay is going to operate. So, whenever, so current will be less, so which is less than that of the rated current, relay looking impedance will be more, so that whenever relay looking impedance is more than that of set impedance, the relay will not operate. Now just check here. What is V by I ratio? V by I ratio is nothing but the impedance Z. What you got? V by I ratio is nothing but the impedance Z, which is nothing but under root of K1 by K2. What is Z, students? What is Z? R plus JXL, which is nothing but under root of K1 by K2. Under root of K1 by K2. Then what is magnitude of this R plus JXL? The magnitude of R plus JXL is nothing but R square plus XL square. R square plus XL square. That is the magnitude of this. Right? We can write. So what is the magnitude of Z? Magnitude of Z is nothing but under root of R square plus XL square, which is nothing but under root of K1 by K2. K1 by K2. If you send this under root, that side, so what happens? R cancel out under roots on both sides. So R square plus XL square is nothing but K1 by K2. R square plus XL square is nothing but K1 by K2. Now if you see this equation, we can write this equation as, so R square plus XL square is nothing but X square plus Y square is nothing but R square. X square plus Y square is nothing but R square. So that which is looking like an circle. So that the characteristics of this impedance relay, is a circle. See here. So this is the characteristics of the impedance relay. Right? These are the characteristics of the impedance relay. So this is R axis. This is the imaginary axis. This will be negative R axis. This will be minus Jx. And what is this point? This point is nothing but set impedance. Right? So this is the set impedance. So whenever relay looking impedance is less than that of this set impedance, the relay will be operating. Whenever relay looking impedance is more than that of this set impedance, relay will not operate. Right? So whenever the relay looking impedance is within this zone, so then only the relay is going to operate. So in this zone, the relay operates. So here relay not operates. Here also relay not operates. Here also not operates. Here also not operates. Right? So this everybody know where the relay is going to operate, where the relay is not going to operate. Clear everybody? Now, so clear, listen everybody. So we are having a transmission line. Suppose this is the transmission line we are having. For this transmission line, we are having the relay here. So it is looking an impedance of ZR. And I have calculated and I set the relay impedance like this. Z set. I got it as 5 ohms. Z set as magnitude of Z set as 5 ohms I got. Now, whenever the fault occurs, very close to this relay, somewhere here having the relay fault, somewhere here we are having the fault. Right. So that the relay is going to see some impedance here. So that the relay looking impedance, for example, ZR. Suppose students, if it is 3 plus J1, it is the relay looking impedance. Then what is the magnitude of this one? 3 square plus 1 square. What is 3 square plus 1 square? Root 10. What is root 10? So 3 point something approximately. So 3.16 or 3.1 for example, approximately. Now the relay looking impedance is 3.1 and relay set impedance is 5. Therefore, as ZR is less than that of Z set, what happens? Relay operates. Up to here it will be okay. Suppose if the fault occurred is a grounding fault, For example, if the fault occurred is the grounding fault. Grounding fault means what is that? Arcing fault. And arcing fault is adding some arc resistance. Is adding some arc resistance. So that if this fault is an LG fault or LLG fault, LG fault or LLG fault. So that fault is going to include some arc resistance, right? So that along with this ZR, we are having some arc resistance. Suppose 3 plus J1 plus R arc we are having. R arc we are having. Now just see here, students. I will continue here. So here, suppose this ZR with arc resistance, it will be 3 plus J1 plus 1, for example. So this is the arc resistance R arc. Tell me, what is this 4 plus J1? 4 plus J1. What is the magnitude of ZR now? What is the magnitude of ZR now? It will be under root of 4 square plus 1 square. It is root 17. What is root 17, students? What is the value of root 17, Durga Prasad? 4 plus something, 4 point something, right? We can write it as 4.1 nearly. So root 17 we can write. Root 17. So we can take it as 4.1 nearly, right? 4.123. 4.123. So ZR is 4.123, okay. Z set is 5, right, students? Therefore, still ZR is less than that of Z set, so that relay operates. Relay operates. Clear, everybody? Now, the fault occurred somewhat close to the relay, and because of that fault, we are having some arc resistance. That arc resistance somewhat close to that relay. That arc resistance is somewhat small, and that will be approximately 1 ohm resistance. So that ZR is still less than that of Z set, so that the relay is going to operate. For example, if the fault occurred somewhat far away from the relay, if you see, if the fault occurred somewhat far away from the relay, this is the relay we are having, it is going to measure ZR. Somewhere here within the transmission line, here we are having the fault. It may be LG or LLG fault, grounding fault or arcing faults. Now, they are going to add somewhat more arc resistance value. So whenever arc resistance is more, suppose the relay looking impedance ZR is equivalent to, actually we are expecting 3 plus J1 plus R arc. If arc resistance is more, suppose if it is 5 ohms. Then what is the value of ZR now? It is 3 plus J1 plus 5. It is 8 plus J1. 8 plus J1. Then what is the magnitude of ZR now? It is under root of 8 square plus 1. It will be under root of 64 plus 1. It is 65. So that it is approximately equivalent to 8.1 nearly. 8.1 nearly. But what about relay set impedance? The relay set impedance is only 5 ohms. 5 ohms. Now, there is a fault in the system. Because of arc resistance, the relay is seeing an impedance which is 8.1, which is more than that of set impedance, so that the relay will not operate. Therefore, ZR is more than that of Z set. So that what happens? Relay not operates. Relay not operates. Are you understanding the point here? So that because of this high arc resistance values, the relay fails to operate. Whenever LG fault or LLG fault which are occurring far away from the relay so is seeing an impedance which is more than that of the set impedance, so that the relay operates. But what is the protective zone? The protective zone of the relay is that this is the protective zone. Within this zone, whenever the fault occurs, the relay has to operate. But the relay fails to operate whenever there is a fault within the protective zone. So this is called as underreach problem. Right? So whenever the relay fails to operate for the faults which are within the zone, right? So this is called as under reach problem. So what is under reach? So whenever the relay fails to operate for the faults within the protective zone, then it is called as under reach problem, right? So if you see the characteristics we have seen, what are the characteristics of this impedance relay? The characteristics will be a circle passing through the a circle as a center as the origin as the center. This is resistance, this is J times of X, and this is minus R, this is minus J times of X. So actually this is Z set magnitude. How much you got? 5 ohms. Now we are having a relay which is actually seeing some 3.1. So this is resistance value and this is the reactance value. So finally we are having this is 3.1. Now because of arcing faults, some arc resistance is added. That arc resistance, this is the resistance, some resistance is added here. So that the overall relay looking impedance is this one now. So this is the relay looking impedance now, right? So previously this is ZR1 initially, Now we are having this is ZR2. As ZR2 is increased and it is more than that of Z set, where the relay is operating, actually the relay is going to operate only within this zone. And where you are having the fault point, so this is the point now, right? So that overall impedance, not fault point, where you are having the impedance point, so this is the impedance point and which is more than that of Z set, so that the relay fails to operate. That is called as under reach problem. Is it clear, everybody? Durga Prasad, are you there? That is called as under reach problem, right? Right. And similarly, whenever the relay operates for the faults which are outside of the zone, then it is called as overreach problem. For example, if this is the transmission line we are having, so this is the protective zone. So that the relay has to operate only for the faults which are in this zone. And here we are having somewhat extra transmission line, and the relay whatever you have connected here, that relay has to operate only for the faults within this zone. Suppose if you are having a fault here, and if this relay is sensing the fault, which are outside of the zone, right? So then that is called as overreach problem. What is that? Whenever the relay operates for the faults which are outside of the zone of its relay, protective zone. Clear, everybody? Right, students? Right. Now we'll see some questions, right? So as Durga Prasad, you asked about some previous questions, right? So we'll discuss some questions here. So here on a radial system, the current setting of the relay farthest from the source should be minimum, and it goes on increasing as we go towards the source according to Indian standards, right? So the Indian standards are fixed, students. So the Indian standard rules we have to study, right? Specifications, the operating value should exceed, has to exceed, so 1.3 times of the setting. 1.3 times of the setting value. So that is the Indian standard settings. So we are having Indian standard book. So we have to, whenever you are going for some of the competitive exams, right? So particularly some TSPSC or any AEE examinations or any SPDCL examinations, sometimes any RRB JE, SSC JE examinations, sometimes they are asking in engineering services also. At least for 2 to 3 years they are asking one question from the Indian standard rules, right? So this question came from the Indian standard rules, so that will be 1.3 times of the setting value. right? So in some of the previous classes, my previous classes, I have discussed some of the Indian standard rules. Just go through that, right? Next one, the value of current or voltage below which the relay opens its contacts and comes to its original position, is called as what? The value of current or voltage below which the relay opens its contacts, it is trying to open its contacts and comes to its original position. So whenever it is coming to its original position, right? So it is opening and coming back to its original position. What is it called as? What is it called as? Any other? Any answer? Any answer? Durga Prasad? Arif? Any answers? The value of current or voltage below which the relay opens its contacts and comes to its original position is called as reset level, right? No. It is called as reset. If you see, students, the total operating time of the relay, will get somewhat clarity about this one. This is the total operating time. Here we got the fault. This is the fault occurred instant. So whenever fault occurred, the relay is going to operate. It is going to give some trip signal to the circuit breaker. So that it is giving some trip signal here. So that at this particular location, the trip signal is sent to circuit breaker. And what is this operating time? This operating time is called as relay operating time. This is called as relay operating time. Whenever relay operating time completes, immediately the CB operating time starts. This is the CB operating time. CB operating time will be in two ways, so two parts. So that will be CB opening time. This is called as CB opening time. And this is arcing time. CB opening time and arcing time. Clear? So here trip signal is received from the relay and CB opening time. So up to here it is, the relay contacts are completely opened. Here relay contacts are completely opened, right? And here arc is fully extinguished. Or we can say fault is cleared. So this time, so from this point to this point, the total time is called as fault clearing time. What is fault clearing time? So the instant when the fault occurred to the instant when the fault is cleared, that is sum of relay operating time and the CB operating time. So when the fault is cleared, so relay contacts are opened, and finally this point, so this is called as relay reset time. So the relay contacts are completely open now. So in the reset time, the relay is coming back to its original position. Relay back to its original position. Right? So whenever the relay is going back to its original position, then it is called as relay reset time. Right? So what they are asking, so the current or voltage below which relay opens its contacts and comes to its original position. comes to its original position is called as what, right? So that is called as the reset level of the relay. Reset level of the relay. Clear? So we are going for the next question here. The tendency of the relay to operate at impedances larger than its setting. The tendency of the relay, it is going to operate for the impedances larger than its impedance. Just check here. So this is the transmission line we are having. The line impedance we are having is 5 ohms. 5 ohms, that is the set impedance. And here we are having an extra transmission line. This is the extra transmission line, and the fault occurred here. Fault occurred here, and the impedance from here to here, it is how much? Some 6 ohms. 6 ohms. Now tell me, if the relay operates for 6 ohms, then it is called as underreach or overreach. Then it is called as underreach or overreach. So whenever if the relay is not operating for faults which are less than 5, then it is called as underreach. They are saying that the relay is operating for faults which are more than its set impedance. More than its set impedance, right? Then it is called as overreach. Overreach. Clear everybody? Overreach. Yes. Durga Prasad. CP opening time is always more than arcing time. Perfect. CB opening time is always more than that of arcing time, right? So that's why I have shown that this distance also. CB opening time is always very high compared to that of arcing time. Very good. Perfect. Overreach. Very good, Neely. Next question. Fuses. Fuses. What is fusing factor? What is the definition of fusing factor? The definition of fusing factor. Fusing factor is nothing but minimum fusing current. Minimum fusing current divided by fuse current rating. Fuse current rating. Right? So that option A is the perfect answer. Option A is the perfect answer, students. That is minimum fusing current, right, divided by fuse rating, right? This is not the statement here. We can remove this statement here. Minimum fusing current divided by fuse rating. That is extra typing mistake. Minimum fusing current divided by fuse rating, right? It's not a minimum fusing current divided by maximum fuse rating. No, right? It is minimum fusing current divided by fuse rating. Fuse rating, right? Right. So identify the correct statement related to a protective relay. Identify the correct statement related to the protective relay, students. So what is the correct answer for this one? A fuse is a device used in circuit for protecting electrical equipments against overloads and or short circuits. Is it true or not? First statement. A fuse is a device used in circuit for protecting the electrical equipments against overloads and or short circuit. Yes, statement 1 is perfect. And a fuse element is that part of the fuse device which melts when excessive current flows. It melts when excessive current flows through it in the circuit and thus isolates the faulty device from the supply circuit. Tell me, is the second statement also correct? Is the second statement also correct? Yes, second statement and first statement both are correct, right? Very good, Power. Very good. Right? So that both statements 1 and 2 are correct. Both statements 1 and 2 are correct. Yes, very good. Both statements 1 and 2 are correct. Very good. Very good, Sai. Sai Kumar. Next one, next statement, next question we can see. So identify the correct statement regarding SF6 circuit breakers. Identify the correct statement regarding the SF6 circuit breaker. First one, the current chopping tendency is minimized by using the gas SF6 at low pressure and low velocity. Yes, perfect statement. So the current chopping tendency is minimized by using the gas SF6 at low pressure and low velocity. Perfect. Second one is the circuit breaker performance is not affected due to the atmospheric conditions. Right? So the circuit breaker performance will not be affected by the atmospheric conditions. Right? Second statement is also perfect. Third one, the electrical clearances are drastically reduced due to low dielectric strength of SF6. No, so SF6 gas is having very high value of dielectric strength, right? So low dielectric strength is a wrong statement, students. So that statement 3 is wrong. SF6 gas is having very high value of dielectric strength. That is the one of the best advantage of this SF6 gas. SF6 gas is having high dielectric strength as well as very low viscosity. Very low viscosity. Those are the advantages of this SF6 gas. So which statements are correct here? So only 1 and 2 are correct. Yes, Sai Kumar. Rated current is nothing but, so actually fuse element decides the fuse current rating, fuse current rating. Fuse element decides the fuse current rating. So if the fuse current conductor is somewhat thick, somewhat thin compared to that of conductor, so the line is having more current capacity compared to that of fuse current. But fuse current now it is having the somewhat less capability, so that it can melt somewhat faster. So that highest possible current, right? So you can say, so the fuse element will decide the what is the current rating there. So that we can say current rating is nothing but the fuse current, right? Very good. Current chopping is very simple in case of, it will be happening in air blast circuit breaker. Very good. It is going to happen in air blast circuit breaker, and it can be easily eliminated in case of vacuum circuit breakers. Right? And in case of SF6 also we can eliminate. How can we eliminate? At low pressure and low velocity. Low velocity. That's what they are saying. Clear everybody? Right. Identify the insulating fluids commonly used for circuit breakers. Which are the insulating fluids commonly used for circuit breakers? Air at atmospheric pressure and compressed air, ultra high vacuum, oil which produces hydrogen for arc extension. Which are true? So which are true here? Identify the insulating fluids commonly used for circuit breakers. Air at atmospheric pressure, compressed air and ultra high vacuum, oil which produces hydrogen for arc extension. So which are true here? Which are true? Which are true here? All 4 are true only, na? So air at atmosphere, air brake circuit breaker, right? And air blast circuit breaker, vacuum circuit breaker, oil circuit breaker, right? So all are correct only. All are perfect. Right, students? So these are the questions we are having. These are the questions we are having in the recently conducted exam, and some students are having doubts about these questions. That's why we have selected these questions, and these are very basic questions only. No need to confuse in these questions. Right, students? So prepare well. So all the best for your preparation. So thank you everybody.